Now that we've investigated substitution and elimination reactions, we have to think about something that oftentimes gives students some nightmares, and that is the rearrangement of carbocations. We now have three different types of reactions where carbocations are intermediates. We've seen carbocations in the addition of alkenes, right? The formation of a carbocation is in addition reactions. We've seen that carbocations form when there's an SN1 mechanism. And we've seen where carbocations form in an E1 mechanism as well. And these reaction pathways commonly yield products that must result in what we call a rearrangement. What do I mean by that? Well, let's take a look at an example. Here I have 3-methyl-1 butene, and I'm reacting it with HCl. And when I do that, if I asked you to predict the product of this reaction, you would certainly, I hope by now, predict that, okay, the pi bond is going to attack the sigma star of HCl. I'm going to form a carbocation. The chloride is going to attack the carbocation. I'm going to get this. And that certainly has been true, and it still is true. But when I actually run the reaction, right, so I would predict this forming. When I run the reaction, I get this, but I also get this. And you might say to yourself, how in the world am I getting this based on the mechanism that I know? And what kind of percentage do I actually see? Well, when I analyze the product distribution, I see that it's the major product of this reaction. So we see that 2-chloro-3-methyl-butane is not the major product, but instead 2-chloro-2-methylbutane is the major product. How do we account for that formation, right? We generally can't just throw chlorines wherever we want to. Well, in order to understand what is happening, we have to follow what's called the mechanistic pathway and come up with a plausible reason for the formation of our new product. So, what are we going to do? We're going to look at the mechanism. And we're going to say, I know that an alkene, the pi bond, right, attacks the sigma star of HCl. The hydrogen-chlorine bond breaks, and I form a carbocation plus a chloride ion, right? Now, this carbocation is a secondary carbocation, certainly, and what happens? Well, the chloride's going to attack that carbocation, and I'm going to get my product. So that is definitely a way that I'm going to get that minor product now. But how do I form the major product? Well, one of the things that we have to look at is we have to look at that carbocation. So let's take a closer look at that carbocation. One of the things that we have to start getting used to is looking at the beta carbons. Now, we've already looked at the beta carbons in terms of elimination reactions, but now we're going to look at the beta carbons even closer. And we're going to see that in this, so for example, in this particular case, this beta carbon has the potential to form a tertiary carbocation. We know that tertiary carbocations are more stable than secondary carbocations. And so what happens is, in the intermediate formation of the secondary carbocation, there's another step that can occur in forming a tertiary carbocation, a more stable tertiary intermediate. How does that happen? Well, notice I've highlighted the hydrogen that's on that carbon. If the hydrogen and its electrons move toward that carbocation, we call this a hydride shift, right? Because the proton and the electron, so the hydrogen and the electrons, that's a hydride, are moving toward that carbocation. So instead of chloride attacking the carbocation, a hydride from a beta carbon attacks that carbocation, and I get this. So now the hydrogen is on that carbon. What happens to what was the beta carbon? Well, it takes on the positive charge. Notice it is more stable, right? Because it has 3 methyl groups donating electron density. So we have now a tertiary carbocation. And now the chloride can attack that tertiary carbocation, and I get the major product. So the only way to explain the formation of my major product is to say that the carbocation underwent a rearrangement. And this particular rearrangement is a hydride shift. A hydride shifted over to the secondary carbocation to form a more stable tertiary carbocation on the beta carbon. And so now that carbocation becomes the alpha carbon in our example, right? Now, it's not as simple as that. Alkyl groups can also migrate to form tertiary carbocations. So again, I look at an example kind of similar to the one I just saw, but now the beta carbon has 3 methyl groups coming off of it. Now I'm reacting it with HCl, and I form a carbocation plus chloride. Notice the carbocation is a secondary carbocation. So certainly I would expect the chloride to attack that secondary carbocation, and I would get this product. But now, based on our knowledge of what we understand about carbocations and their stability, I have to look at the beta carbons. And I see that beta carbon on the right, it could move any hydride and I get a primary carbocation. That's not going to happen. But the beta carbon on the left has 3 methyl groups. Notice if I shift one of those methyl groups over to the carbocation, my resulting carbocation would look like this. Again, I'm going from a secondary carbocation now to a tertiary carbocation, and notice the green methyl group. So the methyl has shifted. The whole alkyl group has shifted to form a new carbocation. And now my chloride ion can come in, and I get a different product, a product of rearrangement. How much product do I get? Well, if I look at the distribution between these two products, I see that I only get 25% of what I would expect to see. I get 75% of the rearranged product. So what do we need to do? Well, obviously the key is to always think if the beta carbon can form a more stable carbocation than the one that initially forms. So that's something that we're going to have to get used to in thinking about. Now, this is with addition reactions, right? So any addition reaction that forms a carbocation, we now have to look at can a beta carbon to that carbocation form a more stable tertiary carbocation? But also substitution reactions can show rearrangements. For example, if I take this alkyl iodide, now in water, so this is a primary alkyl iodide, but we're favoring SN1 conditions, right? Water, solvolysis, you would think, okay, well maybe I can get some type of substitution reaction even though this is a primary alkyl halide. And so what would I expect to see in an SN1 type mechanism? Well, I'm expecting to see this, but obviously I don't see that at all. Instead, I do get a substitution product, and my substitution product is this. And we might go, well, how in the world did that form? Well, again, we have to think about rearrangements. Now, in this case, we have an alkyl iodide and it's not going to form a primary carbocation. And so what must happen is iodide is a very good leaving group, and that's why it was chosen in this particular reaction. It's a good leaving group. So it can come off if it can be stabilized by a nucleophile coming in. Well, the nucleophile is the methyl coming in and replacing the iodide, because in the process I form a stable tertiary carbocation. And now water can come in and attack that tertiary carbocation, and I get the oxonium ion, and now that oxonium ion can be deprotonated by another water molecule, and I form my alcohol. And so you see that even in substitution reactions, we can get rearrangements. So you need to be able to explain, when if I gave you an example where there was a rearrangement, you need to think about the mechanism to form that rearranged product. So we've seen addition reactions undergo, addition reactions forming a carbocation can undergo rearrangement. We've seen SN1 reactions in which, if a carbocation forms, and even when a carbocation can't form, if you're promoting SN1 conditions, you can get rearrangements. And of course, lastly, E1 reactions also show elimination, rearrangement products, right? So, for example, if I take this secondary alcohol and I run the reaction in sulfuric acid and water, right? We're getting E1 elimination of an alcohol. So what's going to happen? Well, I'm going to get this product, right? So I can get three possible products here in this reaction. These are my three possible products. Now, the first one, obviously, we would expect. And the beta carbon on the right has no hydrogens to remove, so I would expect that to be the only product. But indeed, I obviously get more products than I expect, and those products are based on rearranged products. And when I look at the product distribution, I see there's only 3% of my expected product is what I would expect to see. 64% is that tetrasubstituted product, and 33% is the disubstituted product. Well, what's happening in this process? Well, the first thing is, obviously, we're going to protonate the OH group to make a good leaving group. So here I now have a good leaving group, and in water, and that water comes off, and I form a carbocation. Now notice, I form a secondary carbocation, and of course there are two beta carbons. The beta carbon on the left has no hydrogens. The beta carbon on the right has 3 hydrogens. And so certainly I can remove one of those hydrogens with water and form my product. But that doesn't happen very often. Notice, the beta carbon on the left, while it has no hydrogens, it can undergo a migration. This is called a methyl shift, so an alkyl shift, in this particular case a methyl shift, because the alkyl group is a methyl group, is going to shift and it's going to attack that carbocation. Why? Well, because now I form a new carbocation where the methyl group has gone to where the original carbocation is. There are now 2 methyl groups still on that carbon, and that carbon is a tertiary carbocation. Then I can undergo elimination. And notice with this new carbocation, I have 2 different types of hydrogens. I have a hydrogen here in which I can remove that with water and I form my major product, or I have a hydrogen on one of the methyl groups that I can remove with water and form the secondary major product, right? So you see this this occurs often, and so we need to be able to, number one, sometimes predict when rearrangements are going to occur, but number two, And more importantly, especially in this class, if I give you an example where I show you the products and those products result in some type of rearrangement, you should be able to tell me why, based on the mechanism, those products are formed, right? So that's certainly what I'm looking for. I don't always want you to look at rearrangements, but when I show you products that obviously occurred from rearrangements, you should be able to go through the mechanism of that process and determine why those rearrangements occurred.